In today's lesson, we'll continue to look at inverse functions. So this is inverse functions part 2. What we want to do here is to verify that two functions are inverse of each other. We can do that graphically already because we know that the inverse is a reflection of the function over the line y equals x. So in this example, we can see that those are inverses of each other. But how about algebraically? How do we do that algebraically? We know how to find the inverse algebraically, but to actually verify, we're going to use a different process. So let's think about some things first. The point of the inverse is that it is backwards from what you started with, right? It takes you back to where you started from. Remember that function machine? Your input becomes your output, but then if you take your output and put it back in, you have your input. So if you start with x equals 1, you will get y equals 3, for example. And then if you plug this into the inverse, you'll go right back to where you started. It is this property that you use then to prove or disprove that your functions are inverses of each other. To do this, we will compose the functions. We will plug x into one function, plug that function into the inverse function, and then simplify. And verify that you end up with just x. If you don't get x after you compose the functions, then the functions are not inverses of each other. Let's look at some examples. So we want to determine whether the two functions f and g are inverses. You've had some experience now composing functions. We're going to do two compositions of functions here in order to prove that these functions are inverses. The first composition will be that we'll take f of g of x and we'll see what we get. The second composition will take g of f of x and see what we get here. Now I've graphed these so that you can see graphically these actually are inverses of each other. You can see that this point is just this point with the coordinates switched, and this point, since it's at 1, 1, if you switch it, it's still 1, 1. And we could test some others. But clearly you can see these are inverses. But we're going to prove this algebraically. Remember a composition of functions. If you'd like to pause the video and try the composition, see what it spits out. If you remember your compositions of functions, we're going to take our g function, x plus 2 over 3, and we're going to take it and plug it in here first into x in our f function. So we would end up with 3 times x plus 2 over 3 minus 2. Let's go ahead and simplify this function. The 3's cancel. We get x plus 2 minus 2. The 2's cancel and we get x. Based on our definition of inverses, if we compose the two functions and we are left with y equals x, which is what we have here, then we know that these two functions are inverses. But we can't just stop testing it once. We need to actually test it going the opposite direction. So we're going to compose g of f of x. In this case, we're going to take what we have here, our f function, and we're going to plug it into our g function in place of x. So we would have 3x minus 2 plus 2 in our numerator, all over 3. We can see that the negative 2 and the positive 2 cancel, and we end up with 3x over 3. Our 3's then reduce. 3 over 3 is just 1, and therefore we get the x here. By checking both, we can then prove that these two functions are in fact inverses. Let's try a little more difficult example. So we want to determine if these two functions are inverses. And again, I've graphed this for you so that you can see that this point and this point are inverses. Same with this point, and we could pick a couple more here and here. And visually you can see that these are in fact reflected over the line y equals x. So pause the video and see if you can try these two functions and determine whether they are inverses algebraically. Okay, this is a little more complicated. So when you take your g function and plug it into your f function, it looks something like this. both x's are replaced with this fraction, with this rational function. Now what we need to do is simplify. If we follow our order of operations, the first thing I would do is distribute the 2 into the parentheses. After distributing, we now need to combine our numerator together and our denominator together. So we need to have like terms. We can see that the denominator here is, in our numerator, is 2 minus x. So we need for 3 to also be 2 minus x. So we would multiply the top and the bottom by 2 minus x. And we could do the same thing with the 4. Our next step would be to distribute the 3 again into the parentheses. Here we would get 6 minus 3x over our common denominators, and here we would have 8 minus 4x over the common denominator. What's nice about having all 4 of these being the same denominator is we can ignore them. Because if we were to take this and divide it by the reciprocal of this, all these denominators would cancel. So we can just go ahead and cancel those and write this as 8x minus 6 plus 6 minus 3x all over, and this should be an x here, all over 4x minus 3 plus 8 minus 4x. When we go to simplify, we can see that the negative 6 and the positive 6 cancel, so we have 8x minus 3x, which is just 5x. And then our denominator, we have our x's, our 4x and our other 4x here canceling. Negative 3 plus 8 is just 5, and the 5's simplify to 1, and we end up getting x. So we know that f composed of g is in fact x, but now we need to try it the other way. We need to try g composed of f. If you want, go ahead and give this one a try as well and see if you get x. For this one, here we have g composed of f. So I've taken my f function and plugged it in for all the x's. And then in this second illustration here, I have distributed the 4 into the parentheses. And then I've created common denominators for my minus 3. In the denominator, I have a common denominator now with the 2. And then I've taken this negative and I've distributed it into the parentheses. It's important to understand how to do this. Think of your negative as a negative 1. You're only going to distribute it in to the numerator, not both the numerator and the denominator. So now that we have common denominators, let's once again go ahead and eliminate our denominators and just take the numerators from both our numerator and denominator. So we have 8x plus 12, and then we have a negative 3 to distribute. So we would get negative 3x minus 12. Be careful of any negatives to make sure that you distribute all of them. And then in our denominator, we would have 2x plus 8 minus 2x minus 3. We can see up here that our 12s cancel, our 2x's down here cancel, and we're left with 8x minus 3x, which is 5x, and in our denominator, 8 minus 3 is 5. These cancel, and once again we get x. So we have proved algebraically that both of these functions are inverses of each other. Let's go through one more example. Okay, here we have two functions, and you can see right now when I've graphed them that they are not inverses of each other. But let's prove it algebraically. So let's first try f composed of g. So we would take our g function and plug it into our f function. Then we'll go ahead and simplify. 3 times 1/3 is just 1x, and 3 times 2 is 6. If we simplify this, we end up with x plus 4. Since we did not get x, we do not have to try g composed of f. We can stop here, and we know that these two functions are not inverses. We can see that graphically, and we've proved it algebraically. So now you are able to verify that two functions are inverses of each other, not only graphically, or algebraically as well.